Hi everyone. So today we're lucky to have Sheehan Olver as our first international CAM colloquium speaker of the semester. So that's pretty nice. So Sheehan is a reader at the Imperial College London. He's a researcher in computational mathematics. Before that he was at the University of Sydney, and before that University of Oxford, where I met him. He's actually an important part of my education. He was my TA when I was an undergrad. And as a PhD student, I wrote my second paper with Sheehan Olver. So he was a very important part of my career. He won a very prestigious prize called the Adams Prize for his contributions in computational mathematics. And he's kind of known as being ingenious in the way that he uses relationships between special functions. So I hope we get to see a little bit of that today. So I'm looking forward to a talk on computing equilibrium distributions of interactive particles.
All right, thanks, Alan. I think that's the first time I've ever heard you refer to me as a genius, but I guess it's only in a very specific sense of the word. All right, it's a pleasure to be here. It's glad to be able to finally travel again and interact with people in person. And thanks so much for inviting me to give this colloquium. So the colloquium is on, maybe not something that is sort of the core of my research, but something that I'm working on actively at the moment. And I've done things in the past. I'll talk about some work from 10 years ago as well as recent work. So it's on this, when you have interacting particles. So these could be, and we'll actually start in the top with the basic case of like electrostatic particles, where the electrostatic repulsion causes particles to move. But let's say these particles are in a potential well, and you add more and more particles, it eventually will reach an equilibrium, and there will be plenty of pictures in a while. Or you could have sort of attractive repulsive particles, where the interaction is not just logarithmic or Newton interactions, but you have both a repulsive part and an attractive part. And again, when you add more and more particles, you tend to get distributions of particles. So nice, smooth, you do histograms of, you do 1 million particles, you do a histogram, that histogram looks like a smooth curve. And so this talk is really about how do we compute those curves for these types of systems. Okay, so this is sort of the goal. And there's lots of examples. I'll have some nice pictures in a second. You could think of bees, birds flying around. They want to stay together, but they also don't want to stay so close together that they hit each other. They have attractive, repulsive behavior. Bacteria tends to clump together. Space dust, there's plenty of examples. And the question is, can we compute these distributions fast and accurately? So I'll start with sort of the naive approach, particle simulations, and we'll quickly see that this has some clear issues. All right. So instead, we're going to sort of try to understand a bit of the behavior of these distributions, and it turns out using, well, weighted orthogonal polynomials, we can recast this problem of computing a distribution of particles into so actually maybe I'll go to the next slide. So we start with point dynamics. It sort of very naturally leads to a measure minimization problem. So the distribution of particles can be classified in terms of a measure that minimizes some energy. And then it turns out using orthogonal polynomials, we can capture the structure of these measures in such a way that we get sort of sparse systems that are easy to solve and reduces the problem from finding a measure to essentially finding the support of the measure. So we start with point dynamics. The stationary distributions are categorized by measure minimization, which using orthogonal polynomials we can reduce to a low-dimensional, essentially root finding problem. Okay, so this is sort of the overview of what we want to do. All right, so just sort of putting pictures into what I've already said in words. And you can see this all over the place. In nature, you tend to get these nice, when you have many particles with these interactions. Well, I was giving this talk MIT, or some of these slides at MIT, and Alan was not convinced that this looks like a smooth distribution, but to me it looks like a smooth distribution. And if you squint your eyes, maybe it's because his vision is only 95% accurate. So this is an example where the birds sort of attract and repulse. Here's a more physicsy example where space dust or cosmic dust, where the particles attract because of gravity, but then they have fixed size, they can't overlap. That's sort of the repulsive part, which on the microscopic level is actually best thought of as sort of interacting electrostatic. For something a bit more concrete, and to just add a name, so there's something called the Leonard-Jones potential, which is a classic model of attractive repulsive dynamics. And here you think of an interacting particles whose interaction is given by this sort of potential, where it has sort of I probably get them mixed up, but a repulsive term. So when things are very close, they repulse, but when they're far away, they attract. Okay. So you can sort of imagine like a ball, if the ball would roll downhill, but if it gets too close, it gets pushed away. So it's either being pulled in or pulled out. Okay. So let's put things in a very general model. So this is sort of in terms of the point dynamics, this is the kind of equation we're thinking of. So we have sort of a very physics. This is that's the velocity of each particle. So this is acceleration, and we have the different terms. So the first term is, say, self-repulsion friction. So for example, the faster we're going, the more we get slowed down, or a damping term. Here is an interactive potential part. So this, for different potentials, we want to consider how particles interact. This will be the part that has attractive repulsive. And for some of the cases, especially our classic case, we will have a background potential. So this would be the potential well, and these would say the electrostatic interactions. Okay, so this is a very broad model, and there's many possible kernels. We'll start with electrostatic, but really what the new stuff is on this power law kernel, which I'll define in a second. Okay. So for the classic case, let's make this a bit more concrete. So if I have electrostatic potentials in a potential well, this would be, say, V would be, say, x squared for the quadratic well. That's the background potential. Here we have logarithmic singularity, so when we take a derivative, we get this. And you can sort of see that if xk is bigger than xj, it's accelerating to the right, so it's being pushed further away. If it's less, it's being pushed left. And so this sort of captures that sort of attractive, or the repulsive part. So let's see a movie. So this is for those with some damping so that it actually reaches equilibrium. The blue line is the quadratic well. Here's a bunch of particles. They're both repulsing each other, but the well is confining them so that they don't go off to infinity. And we see that over time, it eventually reaches a nice equilibrium state. Now, again, to me, I see a smooth curve. Maybe you don't see it, but if you histogram it, then you do see it. So if we do a histogram of that and actually rescale it, we see very clearly that the histogram looks like a semicircle. So for this very classic problem, particles in a potential well, what we're after is the semicircle, which can be done definitely analytically, but
what do you have the number of particles or?
yeah. So alternatively, probably, I probably should have regenerated them. As things go, you have movies lying around, so you use whatever movies you have lying around. Alternatively, I should have rescaled it so everything has unit mass, so that I should have scaled the charges by 1/n, and then it would also reach equilibrium. But yeah, essentially, here all the particles are are not
You
scales.
have equation you wrote down there, the k. The k is index, right? dk in the equation. The k is the number of, the previous slide, the equation.
Yeah, so there's capital M particles.
Capital M particles.
Each
So
one.
they're moving independently.
Right, and so they interact by,
Interact by. Okay.
everything interacts with each other.
And you don't have diffusion term there.
Diffusion, that's a damping. Is what that meaning.
So it's second derivative that you want to.
What's that?
The diffusion, the second Laplacian.
Well, no, these are particles, so this is an ODE.
Okay.
Okay. So this is a question, how do we go from, say, the potential x squared to this curve? How do we recover from my curve and numerically? So more modern in the sense that people in applied analysis are really sort of active, especially my collaborator Jose and his collaborators are really actively interested in it, is this sort of power law attractive repulsive term. So here we have, and this Leonard Jones is a special case of this. Here we want to be able to do arbitrary powers and ask what, so let's see a movie, and the reason they're interested in it, I guess, is maybe not so much for the application, more of the mathematically interesting behavior. So for example, if our attractive repulsion is this, and we do the same thing, we don't get a semicircle, we get a curve like this. So actually the distribution blows up. Even more interesting, so look at these numbers. This is for 1.45, nothing special. What if we make beta slightly bigger? Now the distribution has split. It's sort of split into two things. So really we want to understand, well, the analysts want to understand this from the analytic level, the actual transition from one interval to two intervals. I think I have a movie later where I show it. I think that's open to some extent on the analytical level, but to understand it, so instead we want to understand it on the numerical level, so we want to be able to compute these blue curves. And then clearly the answer is we can compute it because we did. And then ignore the red curve. The red curve is nonsense. Okay. So that's stuff in 1D, and then and for some reason all my movies are kind of messed up. So this would be sort of a 2D example where you start with particles distributed on a square, and then it tends to this would be the 2D version of a two interval, I think, because it's essentially formed a gap here. So the distribution is some distribution on an x. So we want to be able to categorize this distribution. In case there's anyone interested in stochastics, I just wanted to briefly mention this also comes up in stochastic models. So now here it's actually more of the velocity rather than acceleration, but it still has very much the same features. Here we have the same interactions, but now we have Brownian motion. And in a special case where this is electrostatic, this is something called Dyson-Brownian motion. So this is actually how I first got interested in it, was this connection with random matrices, where, for example, the equivalent of this would be you solve the stochastic Brownian motion. It turns out this also is eigenvalues of a unitary, well, depending on maybe a symmetric or unitary matrix with normal entries, symmetric or Hermitian matrix with normal entries. And if you look at the eigenvalues of these matrices, which are precisely equivalent to this stochastic differential equation, you get the same distributions. And then this is sort of one last example where here is nothing dynamic, but again, I want to connect back to our talk on polynomials. Because these curves are very fundamental, are also fundamental analysis for talk on polynomials, they come up there too. So that's another case where, and again, depending on the weight, if it's a x minus x squared, you get a semicircle. You can think of this as the potential here, v of x4. This would be the point dynamics with the potential x to the 4 would tend to some curve that looks like this. The random eigenvalues of a random matrix do the same, and so do zeros of orthogonal.
Is this a one polynomial or is it a family polynomial?
The family. So you're looking at the large M. I won't talk about that as much. I just wanted to give some of the broader context of this. It relates also to these fields of random matrices, which was how I got into this.
Can you just say again how the weight of the orthogonal polynomial relates to the potential?
Right. So this is usually you would do. So if you look at the family of polynomials orthogonal to the weight v of x, and then you think of it as this as the potential. What happens to the electrostatic equilibrium? It tends to a curve. So that curve also tells you the asymptotics for the roots of the orthogonal polynomials. This is a bit funny because n is also the degree of the polynomial. For things like that, you can just do a rescaling. So I don't want to get too much into that. I just wanted to give some hint that this is a fundamental object in analysis. Okay. So that was, we were talking about evolution of points, stationary states, as well as some other cases where it come up. And it turns out we can categorize it, and this is very natural, comes up from the analysis, but I won't go into the details. We can categorize this as a measure, essentially an energy minimization problem. We want to compute the measure mu over, so there's a unique Borel measure, probability measure, so it's a sort of, think of it as a constrained minimization problem that minimizes this functional. Okay. And this is sort of, this is called the equilibrium measure, especially when it's electrostatic potential, but we use that word for other potentials. And in the case of the electrostatic case, there's two very good books, one by Ed Saff and Todek, and then one by Percy Dice that go into the details of the analysis of this. So this is the problem that we want. So we want to find these steady states, and actually there can be multiple steady states. We'll sort of see this in a picture. The one that we're really interested in is the one that's minimal, that minimizes the energy. Okay. And this is the real question, how do we compute it? So let's say we proceeded naively and we go back to the points, but now instead of time evolution, we try to find, so the measure of discrete delta functions, so we represent the measure of delta functions, so points that minimize this energy. And that's extremely easy to do in, I use a package called optim.jl, but you can use any optimization. So let's say we start with 1 point, add more and more points. Let's see what happens. So of course, it's pretty obvious if you have 1 point, the minimum is going to have all the charges, the only charge at the bottom of the well, because obviously this will have more energy, that will have more energy.
The 1 point, where the 1 point, something that the 1 point in terms of assuming the density is a 1 point or the...
Yeah, so this is saying, what if we, instead of minimizing over all measures, we minimize all...
The Dirac measure, right?
Yeah, exactly. A single Dirac measure.
So you restrict.
Okay. Because this would be sort of the, this is what people tend to do when they solve these problems.
So that's the graph of V, right?
Yeah, this is the potential. So again, we're thinking of these electrostatic. So if that measure minimization problem is not clear to you, maybe it's not clear to me, I don't know. We're still thinking of these as charges, and we want to figure out where to put the charges so that that functional is minimized. So essentially, where is energy minimal? So then, okay, 1 charge is obvious. 3 charges is not so clear. So is this the answer? So these are all local minimizers that the optimization package finds. Here you go, here's the answer. Or is it this? Or is it this? I don't know. I guess you can check them. You can check all of them and figure out which one. What if we have 20 charges? Is it this? Is it this? Is it this? Well, okay, I guess you can check all of them, but there's roughly, if you have k wells, there's clearly roughly n choose k possibilities, because we can move one particle here. It's clearly an optimization problem that's not convex. You can just see it. It's very clear. It's an optimization problem that's very non-convex. There's many local minima. And so trying to do this on a discrete level is sort of a no-go. Okay. So now I'm going to show you how to do it using orthogonal polynomials, but let's just see what the answer looks like to get more of a sense of how challenging this might be. So this is that same potential with three wells, and this is the answer, the distribution of charges which minimizes the energy for different scalings. So even though it's the same thing, depending on the alpha, you can either have one interval of support, two interval supports, even three, and then suddenly it switches to one. So some of them, so that plot I showed you might have been the answer was to put them all in the far right. Well, I can't remember what the answer was. But this sort of sends us this picture. Once you see the answer, you sort of see some indication of where we're going to go with this, which is that in each component.
Are you increasing alpha in the video or decreasing?
Oh yeah, I guess it's very small. It's hard to see.
Okay.
This is 300.
And you're decreasing alpha?
Yeah.
Okay.
So I'm.
So you're making the well deeper?
Right. So when these wiggles are really small, the charges just swamp it.
Okay.
And so then there's only one interval of support. As these wells got bigger, like it's sort of intuitively you can see that if this well is super, super big, then it's going to be so much bigger than these other ones, so then all the charges have to live there. Okay. But the key feature that we're going to notice is that this is precisely square root singularities. And so this is precisely that semicircle, which was the canonical case where we can actually get pretty easily with analysis, times something smooth. Okay. So that's going to be where we're going with this. For how do we compute these numerically? We're going to write it as a smooth function times something with square root singularities, and it's very natural if you're an orthogonal person, polynomial person, which I am, and really this whole talk is just an excuse to talk about orthogonal polynomials. Who cares about these applications? I really like the orthogonal polynomials part. You want to expand it as square root times the related family of orthogonal polynomials. Okay. So that's sort of the introduction. The rest of the talk will be a little bit more technical. So if you want to fall asleep, now's the time. But wake up at the final section. So I'll remind everybody to wake up.
So the second you did is just one dimension on real dimension.
Yeah, I'll do examples on higher dimensions.
Higher dimension?
Yeah.
Okay.
So we can actually, I'm not going to go into much detail. We can do balls in arbitrary dimensions with power law kernels. So we can't yet do the annulus where it splits, but we can answer the question for when the support is ball. Okay, so this is sort of the sketch. So I'm going to do a brief introduction of orthogonal polynomials, and really how we use them to get sparse discretization, because that's essentially what we want. Is we're going to recast that minimization problem as a linear problem with unknown parameters being the support. We want to discretize it sparse so that we can solve a linear problem efficiently, and that's going to give us very accurate, spectrally accurate numerics. Okay, so this will be in the context of differential equations. That will be very brief. We'll see how we can get sparse discretizations for, in the potential theory case, for these basic singular integral operators. So using orthogonal polynomials, we can turn a singular integral operator, which is a non-local operator, into a sparse discretization. This will then lead naturally to the problem I said I was going to solve, which was continuing these equilibrium measures. That is, put enough structure that we can really make it tractable. And finally, this is really the new stuff, which is how, using orthogonal polynomials, we can also do sparse discretization with power law equilibriums. And the last part is I wanted to mention some broader applications beyond this sort of special case to PDEs. To essentially integral reformulation of boundary integral reformulation. So hopefully this is a review for people. They sent out this note about how to give a good colloquium, which has assumed that people know nothing, but I think there's only so much you can assume that. So here we're going to work with orthogonal polynomials given a weight, and this is a very basic property that we're going to use, is that orthogonal polynomials satisfy the three-term recurrence. And really that's a big theme here, is recurrences lead to sparse discretizations. Essentially that's our goal, is find recurrences for these other integral operators. Here's the families of orthogonal polynomials we need to work with. The first is Chebyshev T. I hope anyone who knows Alex knows this, which are, we can write as cos and arc cos x, which are orthogonal with respect to this weight. This one is sort of slightly more useful for us, because these are family of polynomials that are orthogonal with respect to the weight. The weight captures these squared singularities. So we want to represent these measures in each component as a polynomial expanded in this basis times this weight. Finally, we will also, especially for the power law stuff, we need ultraspherical polynomials, which are sort of, for integer cases are derivatives of these, other cases are not, but they are sort of 1 minus x squared to power lambda minus a half. Okay, so these are our family of orthogonal polynomials. And so our angle of attack is in each interval of support, if we knew the interval of support, we are going to write the measure as a linear combination of these orthogonal polynomials times associated weight. So this is just an affine transform from -1, 1, where they're defined to the interval a, b. Okay. And power law will be the same thing, but with ultraspherical. Okay, because it turns out that's the right singularities for those operators. And so our goal is to recast this energy minimization problem to a more structured problem of find A and B and Cn. Cn. Okay. So that's our angle of attack. The important thing is this is a linear combination. Mu is a linear combination of Cn times some functions. Okay. So how are we going to use this? Well, we have a minimization problem, which one could think of solving with gradient descent or otherwise. But in our case, it's going to be helpful to recast a minimization problem as a root finding. So if we had, say, the one particle case, we would just obviously differentiate, and we could find the roots. And the reason this is helpful for us is sometimes there will still be multiple measures that solve the equations we end up with. There could be, say, one supported there, one supported there, one supported there, one supported there. We might still have multiple measures. We need to figure out which one is the right one. It's not going to be n choose k, it's going to be a small number. By going to root finding, we have access to not only Newton iteration for finding one root, but we can find all the other roots using deflation. So I'm not going to say anything more about that, but it's just an important point why we want to go from minimization to root finding. Okay, so that's minimization with one particle. For measures, the analog is this. So there's something called the Euler-Lagrange reformulation, where instead of finding this, instead of minimizing this, we can solve this equation where x is on the support of the measure. So essentially this term, and this is just a kernel times our measure, we have in our mind the answers of the measure is the sum of Cn. B is equal to some constant. We don't know the constant. Okay. And then we finally get to the root finding problem by differentiating this. And here I'm writing everything in 1D. So this is sort of our angle of attack. We have our ansatz. We know from the simulations that square root times smooth. this is our equation, and here is the key point, is if we knew A and B, if we know the support, this is a linear problem. So this is linear in those coefficients Cn. So essentially we've recast this energy minimization problem, which is hard, to something that seems more tractable. Just find A and B and solve this linear equation. So it's a linear equation involving these integral operators.
And here x has to be in the support.
Right, right. Yeah, I
Which
probably
you
should have
don't
wrote
know.
that, x in the support.
Which you don't know.
We don't know the support, but we've guessed that, say, we guess that it has one interval or two intervals. Then it's a question of find the support. If we know the support, we can solve it. So we need to, so that's, the Newton iteration is only on the support, right? But each step of the Newton iteration will involve solving a linear singular integral equation. Okay.
I think I missed the fundamental step. So where did you tell us how to read off the type of singularity from the interaction kernel?
Well, in the log case, it's square root singularities.
You told us what it is in each case.
In power law, it falls out. It actually falls out from making this nice. So the numerics actually tells us, making the numerics nice tells us what the singularity is.
Okay.
So that we'll actually come back to that.
Yeah.
Then.
And the choice of the numeric doesn't depend on the singularity. You didn't say that the weight measure you pick up for the orthogonal polynomials.
Well, so we're taking as an ansatz.
But you have differentials of orthogonal polynomials.
Right. Here, in the log kernel case, we know it's square root singularity, so it's natural that you should you. In power law case, it's we know that it is 1 minus x squared to some lambda. We don't know the lambda, but the lambda actually falls up out of this equation. Yep.
What would you do if you were in like 2 dimensions?
I'll talk a bit about balls. If it's not on a ball, if it's not radially symmetric, I don't know. So if you don't tell me. Okay. So that's our problem. We want to solve a linear, putting aside the finding A and B. We have this problem. We want to discretize a singular integral operator in a way to make that efficient to solve. And so this was sort of when I was doing this in the electrostatic case 10 years ago. I had sort of set the orders wrong. I guess I was working on this paper, but also working on that paper since that paper was 2011. But maybe it's the other way around. But anyways, I was also working on these ultra-spherical spectral methods where Alex and I saw that recurrence relationships lead naturally for differential equations to sparse discretizations of differential operators. And so the goal was, we want sparse discretizations using orthogonal polynomials for these integral operators. Can we replicate this and find recurrence relationships that they satisfy to make things sparse? So, and these are really the, for the electrostatic case, these are the things we want: the log kernel plus its derivative, which is the Hilbert transfer. Okay, because we differentiate, and that's okay. So in the just to make it slightly more concrete without getting too tedious, so example from the ODE case is, this is what I mean by a recurrence relationship. We have these very sparse recurrence relationships for, I'm only writing the Chebyshev T ones, also for ultra-spherical for higher order derivatives, and they immediately gave us sparse discretizations of differential equations. And our hope is to do this exact same thing, but with singular integral operators. Essentially, we want to find formulas like this involving ultra-spherical polynomials with log or power log kernels. Okay. And so there's two big themes, that two messages that are lying here. Why we want to go down this route. One is these are non-local operators. But doing this route, we turn them into banded. They become local in coefficient space. Another important thing is that I at no point will discretize integral operators. So by working with recurrence relationships, we get sparse discretizations of sparse representations of the operator, but without ever having to approximate an integral. Because singular integral operators are nasty, where this way of doing it avoids that sort of nastiness. Don't make it for time. Okay. I guess I want to stop at 20 past, is it?
Yeah, 20 or 25 past.
Okay, so these are the operators. I want to figure out, so I'm just going to do gentle example with sort of Hilbert and log kernel. That actually doesn't matter. Ignore that. Okay, so how do we get sparse recurrence relationships for these integral operators? So, and this is, I guess you want to have like, at some point you want some mathematics, even if it's very basic. How do we find a recurrence relationship for the Hilbert transform of a weighted orthogonal polynomial? It turns out, so we have this three-term recurrence that I mentioned before for orthogonal polynomials. If I just put that inside the Hilbert transform, do x minus t plus t, that's t times pn, plug this in. This is sort of the beauty, is the Hilbert transform satisfies the exact same three-term recurrence as orthogonal polynomials themselves. Okay. So these are the exact same coefficients as those, apart from a different initial condition. Okay. Another bit of magic is, and this is why these end up being the natural weights for the log kernel case, is that the Hilbert transform of the Chebyshev t weight is 0. And putting these together tells us this beautiful recurrence, it's sort of a one-term recurrence, that the Hilbert transform of weighted Chebyshev t is Chebyshev u, and the Hilbert and this one is actually more important because our expansion is in terms of that. Hilbert transform of Chebyshev u is minus Chebyshev t. Okay. So these are sparse recurrence relationships, which essentially tell us that for the equation we want to solve, we get the sparse, actually, essentially diagonal discretization. This part we're not going to use so much. I just wanted to put it up here for completeness. Is we can also do log kernels. We can also get sparse, in this case, actually diagonal relationship for log kernels. Also for Chebyshev u, but I'm not putting it up here, using the fact that the Hilbert transform and the derivative commute. Okay. So essentially, for the log kernel and Hilbert transform, the ones we need for the electrostatic particles in an electrostatic well, we've sort of solved the problem. We've figured out that as long as interval is supported, is one interval. So that tells us the linear part. We still need to talk a bit about how we choose interval of support, but it's fairly straightforward now. So again, just to repeat what I already said, we want to minimize this. This leads to the Euler-Lagrange reformulation. There's actually two parts, is that this is constant on the support of the measure. For it to be minimal, it has to be greater than or equal to the constant everywhere off the support. The key thing we do is ignore this. So we find all solutions to this. There might be more than one. We can use deflation in the case that there's more than one. And then we can use this to check that we've gotten the minimal solution. Okay. So then we take this and differentiate. The L disappears, this unknown constant, and we get Hilbert transform is equal to V prime. We expand if there's a single interval in this Chebyshev u, and now using that three-term recurrence, we know how the Hilbert transform acts on the spaces. So our system is as simple as can be. Okay. So this is how you invert the Hilbert transform. You expand the right-hand side in Chebyshev t, and that tells us immediately the solution, the coefficients of the measure. Except we have two constraints, which is perfect. We have two unknowns, the interval of support. It sort of worked out perfectly that we have two constraints. One is this needs to be invertible. So this is only invertible if that coefficient is 0. So that tells us one constraint. The other condition is it needs to be a probability measure. So essentially, the integral of the measure needs to be 1. So that tells us the second constraint. So we have two unknowns, A and B, assuming that the interval of support is a single interval. These are embedded in these coefficients because these are mapped coefficients. Two conditions, and then we choose those two conditions, constraint, two unknowns using Newton iteration. Okay. I should mention auto-differentiation is really your friend here because you can auto-differentiate the expansion of Chebyshev coefficients to get Jacobian, so it's actually quite simple. Okay, so that's the one interval case. Two interval is a bit more complicated because we use each expansion on each interval separately, but these integral kernels are non-local, so they feel each other. So we have to consider the expansion here evaluated over there, but the kernel is singular on its own interval, but if we have a function supported on only this interval and evaluated over here, that kernel is smooth. So essentially we know it can be approximated low rank, or it's a compact operator. Essentially, it's well approximated by a finite dimensional. So now we have two unconditions. Using that, what I just said, we can solve the linear part. We also have two n constraints. The linear system needs to be solvable. There's going to be n conditions, so that's equivalent of that v0 being 0. We're going to have n of those, one for each interval, but they're all sort of jumbled up in the linear system. It also has to be a probability measure, and we have n minus 1 conditions that this L, this constant, has to be the same on each interval. Okay. But anyway, so just to give some picture, so if we have the Hilbert transform on 3 intervals, representing each one as a Chebyshev U expansion, we no longer just have the diagonal part, we have this finite dimensional part corresponding to the communication between the intervals. But we get a still nice sparse system depending on how close intervals are that we can solve, and alongside automatic differentiation, choose those finite Jacobians for those unknowns. So that's sort of the end of the story, and going back to this example, this is exactly how we compute those measures. So here's a picture of the support. Here's one interval. We have two unknowns. These intervals, we can use Newton iteration to find them. Here, we have two, and you have to take into account that there's communication between them, but that's low rank. Yep?
So do you use numerical approximation to construct that matrix? So you don't have recurrences between two intervals?
You actually do have recurrences, because those recurrences are valid on and off, this is a key point, off the support.
Okay.
So essentially, if you know the first column, which in this case, you're actually, it's what is it, x minus square root x squared minus 1. It's actually, each column is the Chebyshev coefficients of x minus square root x squared minus, or 1, x squared minus 1 to the power k. So in some sense, you have an explicit formula.
Okay, except like Chebyshev formulas explode off their input, but I guess you're only using the recurrence coefficients, so you don't actually touch.
Right, so you're assuming there's some separation in intervals, so then that it's smooth. Okay, so that's sort of the stuff 10 years ago. Now we want to do these more interesting, attractive, repulsive kernels. So we want to do this with power law kernels. And really, essentially, the message from those previous slides was it's all about a sparse discretization of the single integral operator. So the actual computational measure follows the equivalent. Okay. So we want to find a recurrence relationship for this power law kernel. So before it was the Hilbert transform, we did x minus t plus t, and it had the exact same three-term recurrence. For this one, well, I do what one does in this situation. You look at the DLMF, and there's nothing other than gibberish. So it's not very good, though. These fractional integrals give you some hint of how you might do this. So the way we're going to do this is split the power law in terms of a sum. So we have absolute value x minus t. This is a sum of a left part plus a right part. And by doing the split, we'll be able to get a recurrence relationship for each part separately that we then put together to find a recurrence relationship for the power law, which tells us how to get sparse discretizations. Okay, so how do we do this? Well, we try the exact same trick that worked so well for the Hilbert transform case. We multiply x times, this is a fractional integral operator. We do x minus t plus t. Okay, so far so good. T times Pn satisfies that three-term recurrence. But we've sort of shifted the power. But for classical orthogonal polynomials, so this fractional integral is a real, a normal integral times q alpha. And for classical orthogonal polynomials, we have recurrence relationships for integrating weighted orthogonal polynomials. And so everything works out so that this is not the same three-term recurrence, but it's one that we have explicit formulas for. So for the left-sided one, it's fairly straightforward to get a three-term recurrence. For the right one, it's also fairly straightforward to get a three-term recurrence. And putting those together gives us a three-term recurrence for the, oh, I don't know what just happened. I must have pressed the wrong button. Putting them together, we get this, this theorem. And so this is for any, and this is an important point. For any lambda and any alpha, we know that this satisfies a three-term recurrence. Okay. Well, I meant to delete those points, but you can sort of see. Okay. With explicit formulas. So the first time I said, I gave this talk, I said, new question mark, probably not, because this is the sort of thing that must have been in some ancient Russian paper. Then we got the referee report, said, you forgot to cite this ancient Russian paper. But that ancient Russian paper had only a special case when it wasn't for any alpha and lambda, it was for a specific lambda and alpha pair. So this, I'm more confident that it's actually, that even the ancient Russians don't know this formula. Okay. So then, that tells us a three-term recurrence. It doesn't tell us sort of, we're not yet done because we need it to map from weight ultraspherical polynomials to essentially a polynomial right-hand side. So before we had Hilbert transform times weighted Chebyshev U was equal to polynomials. That's how we knew that was the right weight. So we want to choose the weight so that the operator maps to polynomial. So if we have a smooth right-hand side, it's going to capture that. And without going into the details, this is, to answer your question, this is how we know what the singularity is by choosing it so that our operators map to polynomials so that we get sparse discretizations.
Okay. So your polynomials, they are again function of some linear operators.
What's that?
The polynomials you are using are again function of some linear operators.
Yeah, but we don't use that.
And do this linear operator has some property with the fractional derivative to make this relationship
Not that I know of. I mean, maybe.
Augmentation or something like that.
All right, so then that's only one of these. For the tractor repulsive, we have we have alpha and beta. So here, what we do is we construct the basis to make one of these banded, and fortunately, the other one becomes approximately banded. So the other one is no longer banded, but it's exponentially, it has exponential decay, or maybe it might be algebraic, but it has fast decay at the diagonals. And therefore, for these attractive repulsive kernels, absolute value x minus y to the alpha minus x minus y to the beta, we get effectively sparse discretizations. And we can solve invert with these operators, and then the other part, choosing the support, becomes a single digit variation.
Isn't that a big surprise? Because they both cause different singularity types at the edge.
Yeah. Well, yeah. So you use the basis with one of the singularity types, but it ends up being quite effective. So whichever one of these is dominant, basically. Okay, I'm going to skip that. Okay, and then, because I'm running out of time, so then this all extends to higher dimensions. I won't go into details, but you use multivariate orthogonal polynomials, so multivariate analogs of ultra-spherical polynomials, which are polynomials that are orthogonal in a ball or a disk, 2D. You can recover recurrence relationships, sparse recurrence relationships, and then get sparse discretization for these power law kernels applied to the multivariate polynomial extensions. So it ends up working out very, very cleanly, like the one we used. All right, I don't have much time. I just want to mention briefly that this works for other integral kernels. So for example, general, say here's some PDE, if you do a boundary integral reformulation, general integral kernels always have the feature, this is part of Green's representation theorem, that they're log kernel times something smooth plus Hilbert kernel times something smooth plus something smooth, and that we can use to get, using the same ideas, get sparse discretizations and solve, say, these sort of PDEs using the same techniques to get sparse discretizations. Okay. And I'm going to leave it as an open question. Maybe someone in the audience knows a good example of, are there examples where you get power law kernels on in this setting?
How do you get this support? Support is part of your computational procedure where you discover this support, or you have to a priori know this, or what?
No, the support is unknown. The endpoints of the support are unknowns in sort of the Newton iteration. And the constraints that need to be satisfied fall out of the linear system. So you get a sparse linear system, you need to satisfy some constraints.
So do you need to know I have support 3 intervals or 5 intervals?
Yes, you need to have ansatz.
Okay, so you need to know that.
Yeah.
A priori. Okay, so like here, you need to know 2 holes.
In the well case, you can try one interval. If one interval is not enough, it'll go negative, or it won't satisfy and then you try 2, then you try 3, and so on. So you can do an iterative procedure. I'll just mention in terms of future applications, so I don't know applications with power law kernels. But we are looking at, so there's a deep link between these fractional power law kernels and fractional Laplacians. That they tell us essentially they're the inverse of the fractional Laplacian. Here, there's a number of applications, and sort of ultrasound is one we're looking at, as well as crystal electric fluids, length, and equations for plasmas. Here's one fun toy example, which I'll sort of, I guess I'll leave at this, which is why you would care about fractional calculus, because a lot of people probably don't care about it. Here's one where it's natural, is that if you have a levy flight, this is like Brownian motion, but with heavy-tailed jumps. So this is actually Cauchy jumps. You get these piecewise continuous, and you can ask the question of, given a set, what is the how long does it take to leave the set? So here, it's piecewise continuous, so it's possible to jump between components, and that's precisely given in terms of these fractional Laplacians. So I think it's like the conclusion is this gives us a powerful technique for getting sparse discretizations for power law kernels, fractional Laplacians, with potentially many other applications that I don't know of. And so if anyone has examples, please let me know. Also, we just live attached to this grant, we're advertising the postdoc. Okay. Thank you.
Thank you very much. Any questions?
I thought at the end you were going to, so it's a comparison of the density you compute and you estimate for a flock of birds or bacteria aggregation. Have you tried to do that?
Yeah, I mean, I guess so. Those are sort of the thing is, there's obviously no physics that model birds. So this is sort of a parameter estimation question that these. So even the Leonard Jones potential, that doesn't actually come from physics. That comes from sort of an artificial model that's meant to capture the physics of attractive repulsion. So so it's sort of, it's more of, those kind of things are sort of inspiration for these slightly artificial in that they're not directly tied to the birds, at least at this level, which generate very interesting mathematics. So that's sort of my understanding of them. So people in applied analysis are definitely interested in these types of things, probably more on the mathematical level rather than just trying to understand how the equations behave. The last stuff, which is sort of work on progress, like ultrasound, is more sort of more concrete in terms of applications.
So this also a polynomial also for infinite intervals, half infinite, something, or just all with finite?
Yeah, I mean, that you can do half. I mean, there's obviously Hermite polynomials, and things get a bit more tricky for these single integral operators for Hermite polynomials, but that's sort of a slightly technical point.
So in your first example, you had an alpha that you were varying, and you were seeing the bifurcation of the one interval 2 and then 3.
Yeah.
Are you able to actually tell me when the interval splits, as opposed to just compute when there's 2? It seems like your 2 interval case breaks down when the intervals get too close.
Right, I mean,
How does that work?
it's clearly not so bad in that I made this picture. So it does break down in that that complex part, the influence on one interval on other becomes dense, but if you just truncate naively, it does it's good enough job for plotting accuracy. It's actually possible to, if you start going outside classical orthogonal polynomials, you can do the same thing if you say let's say you have 2 symmetric intervals with a very small, this is say rho minus rho. This is sort of the 1D analog of an annulus. If you use polynomials orthogonal with respect to this, so as rho goes to 0, this becomes a Chebyshev weight. Then everything is nice. You get banded operators, and it's robust as rho goes to 0. So in theory, there are ways to make it sort of robust in that difficult regime. Because then the Hilbert transform for orthogonal polynomials in this diagonal done.
Okay. Go ahead.
So the in the 2 dimensions, you have like the kind of like distribution of particles, right? Is there something in 2 dimensions that works like the fact that the roots of the 1-dimensional polynomials are in the same?
That's a really interesting question. So you mean the distribution of the roots of
Yeah. Like
polynomials?
my understanding was that in 1 dimension, the roots of the polynomials were distributed like the.
Yeah, exactly.
But in 2 dimensions.
So this is actually this is a really interesting question because of so it's hard to roots of so orthogonal polynomials in higher dimensions are only defined up to their span. So the degree m polynomials, there's no canonical basis. It's just the span is canonical, which means that there's no real notion of zeros of it's, at least as far as I know, there's no analog of something as fundamental as roots of orthogonal polynomials in higher dimensions. There's a really interesting analysis question, which is equilibrium measures are first step on asymptotics to orthogonal polynomials in 1D. Are these types of measures a step towards, because there isn't really anything on asymptotics for multivariate orthogonal polynomials, at least in general, is this potentially a step towards this? Is this somehow the thing that tells us what the asymptotics will behave like? That I don't know. So that's an interesting question.
Okay, let's thank Sheehan again.